So we've got Marion and Andrew worried about all of the water gathering on their patio now. Sort of a real life situation. This might be your aunt and uncle or your sister and brother-in-law and trying to work out what's happening. So let's see if we can apply a bit of our maths to a real world problem. So on this page, I've just shown the first couple of parts of the question to get us going because we'll run out of space otherwise. So the first thing we've got to do is to find the form of a linear model using logarithms. And the model which we're told to work with is d equals p times q to the t. So if we take d equals p times q to the t and take logarithms of both sides, using our log laws, we get log d is log p plus t times log q. Now the variables in this are, in the original model, are t and d, and now in this linear model, the variables are t and log d. We'll come back to that later. So now we've got to code the data appropriately according to this model. Log p is the y-intercept. That's the sort of y equals mx plus c. So log p is the y-intercept. That's the c here. And the gradient is log q. Again, we'll come back to that. So part 2, code the data appropriately. So if we draw up a table, so in this new model we're plotting t against log d. So that's why we need to just code the d's to log d's. We don't need to code the t's to log t. So what are the values of t? Well, the question stresses that t is measured in hours, and because the measurements are taken every 12 minutes is 0.2 hours. So the values of t start at 0.2. So we've got the values of t there going from 0.2 up to 1.2, the 6 measurements, and then when we put the values of d in, we've got those values of d which are given in the question, and calculating the logs of those numbers gives us these numbers here, 4 decimal places at this stage. So that's the data coded appropriately according to the model. So now we move on to the next part of the question. So we've got 4 more parts to go. We've got to calculate the product moment correlation coefficient for the coded data. Well, if you put that data on the previous table into your calculator, you should get a PMCC of minus 0.9970. How does that verify their belief? Well, because that's very close to -1, that shows that the coded data is very, very close to a straight line. And the coded data is the linear model. So that verifies the belief in the model that was originally proposed. And that's the model that was originally proposed, d equals p times q to the t. So now we need to find the values of p and q to 2 significant figures. Now, if you've popped the data into your calculator to find the product moment correlation coefficient, then you should also be able to, using the calculator, get the values of the y-intercept and the gradient for the linear model. And when we compare that with the version of the original model, but taking logs of both sides, we can see, as we mentioned earlier in the question, that log P is 0.4736 and log Q is minus 0.5982. So log P is 0.4736, so P is 10 to the power of 0.4736, which is 3.0, so two significant figures. Log Q is minus 0.5982. Q is 10 to the power of that, which is 0.25. Part 5 asks us to use this model. Oh, we need to write down what the model is. So that's the model with those values of P and Q substituted into their correct places. So part 5 now asks us to predict the depth of water after 4 hours. And when we put t equals 4 into the model, we get a prediction of 0.01 centimeters. Is that prediction a reliable prediction? Well, the answer is no, because the observed data only goes up to t equals 1.2, and we're using or trying to use the model as a prediction of the depth when time is 4 hours, so it's not reliable. So there we are.